Hello, Paris. Um, I'm Luyan from UT Austin, Department of Physics. My supervisor is Dr. Thibault. I believe he already gave the talk a few days ago. So my talk today will be about metastable spiking networks in the replica-mean-field limit. So right now it's 3 a.m. here. The networks in my brain is not in the best state, so bear with me if I make any mistake. An increasing body of experimental results supports that synaptic strength, synaptic inputs impact the neural response individually rather than their population averages. However, traditional thermodynamic limits rely on synaptic couplings that inversely scale with the neural network size. These limits fail to reproduce realistic neural variability, which is shaped by finite size effects. So we use replica-mean-field limits to address this point. Based on our proposed model, we can further study metastability captured by this limit. So here's a finite size network. Conceptually, we map this network into a limit network, which we call the replica-mean-field limit network. This network is made of an infinite number of identical copies of the original network. When a neuron spikes, for example, number 3, this spike is dispatched uniformly randomly across our replica. For example, this 2' and 1' receive the spike. So this is the main concept of the RM limit. This similar complication actually allows us to have a tractable set of equations mathematically. Because when we take the number of replica to be infinite, we erase the correlation and every neuron receives Poissonian input. So here's the specific neural model we use. Basically, we treat each neuron as an object with stochastic intensity, lambda t, which is the instantaneous firing rate of the neuron. There's also a point process associated with each neuron, marking the spiking time. And specifically, the dynamics of the stochastic intensity is governed by an internal variable x of each neuron. When a neuron receives spikes, the synaptic strength is added to its internal variable x. The strength can be either positive, indicating it's an excitatory input, or negative, which means it's an inhibitory input. When a neuron spikes, x resets to 0. There is also relaxation or leakage, which means when the neuron is in between any spiking events, x will decay exponentially to 0 with some time constant tau. And finally, this internal variable x is related exponentially to the stochastic intensity. So the choice of this exponential function is made mainly due to both experimental relevance and the ability to take positive and negative synaptic strength to account for excitation and inhibition at the same time, because we need the stochastic intensity to be a positive number, or non-negative number. So now we are able to write down the time evolution of the internal variable x. Here, actually, what we did is we considered the time evolution of e to the ux, since we are aiming for an equation of the moment generating function of x. So on the left side is the change of the exponential from time 0 to t. And on the right side, we have the 3 dynamical components. The first term represents the update upon receiving spikes. The second term represents the reset. The third term is the relaxation. This equation is highly correlated, and here is how the RM limit plays a role. In RM limit, the deliveries of other neurons becomes asymptotically Poissonian. So the point process nj in the first term and second term, just the first term, representing the spiking of other neurons, becomes a Poisson process. And now we can assume the system will enter a stationary state and apply the rate conservation principle. So we get this equation on the moment generating function of x. So in this equation, there are both derivatives and non-local term, which means we have a delayed differential equation. Well, it's actually an advanced equation, but we can just flip the sign of u and it becomes like, since u here is not really a time. The peculiar part of this equation is the presence of this beta I here, which is the mean firing rate of the neuron I. So to solve beta I, we need to know the solution to Li. And to solve Li, we need the value of beta I. Basically, we need to solve it self-consistently. For traditional DDE, usually we have an initial function, but in our case, we don't have one. It turned out that the uniqueness of our solution is determined solely by the regularity that we require for moment generating function. It was kind of hard to solve, but we did it, and we can write down the replica-mean-field equation for the mean firing rates. So on the left side is the mean firing rates of neuron I, and on the right side we relate all the mean firing rates of other neurons to that by an infinite series. And we can view this as a singular expansion around the parameter h, which is the base rate of the neuron firing. And this series is highly divergent, but fortunately, we can compute or evaluate the value of this series using Poincaré approximation in a certain parametric range. For each neuron, we have such an equation, and in total, we have as many equations as the number of neurons in the network. So if we solve all these equations iteratively, we can get the mean firing rates of the entire network, and with which we are also able to compute the higher moments. So basically, at this moment, you can think of our model as a machine that you can input the topology of the network and output all the moments of the stationary dynamics of the neuron. So here is some results of our models. Basically, this slide shows that using our theoretical RM calculation is much more efficient to do. We can just look at the rightmost figure. The simulation, the RM calculation is taking 2 orders of magnitude time less than the simulation. And as a single check, you compute the rates of the 2 networks. On the right side, we have the connection matrix with color indicating the connection strength. And the calculated rates and simulated rates are shown on the left side. They are agreeing with each other very well. We should stress that the simulation is for the exact original finite size network, but the RMF calculation is calculating the rates for the limit network. The fact they are agreeing with each other is very amazing. We can also do a quick moment analysis here. We compute the output rate of a single neuron subject to varying strengths of exciter input. On the left side is the mean fire rate. So the red dots are from simulation. There's a yellow line, which is our RMF calculation, following these dots closely in certain parametric range. That's the range that our method converges. And these green and blue lines are from TMF, thermodynamic mean-field limit. They only capture the behaviors of the system in either small or large area. So similarly, we have the same behavior for the standard deviation. Okay, now the fun thing, we consider this network shown on the top left. It consists of 2 identical sites, where each site consists of a cluster of excitatory and inhibitory neurons. Because of the symmetry of this network, there will be 2 cases. One is the rates of the two sides are completely the same, which we call it the monostable state. The other is we have a bistable state, where the two sides are competing against each other. As we change the parameter of this network, we should be able to control which state the system is in. So in this plot down here, we change the connection strength among excitatory neurons and plot the mean fine rates of neurons. As we increase it, the system goes from monostable regime to bistable regime. Here, the solid line is from our RMF calculation, and the dots are from simulations. And here on the top right corner, we plot some traces from the simulation. We can see the two very different characteristic features in monostable or bistable regime. So the one thing our method can do, but not a simulation, is that it can capture the behavior of the system in the regime where it's the switching between monostable and bistable states. In this regime, it's hard to use simulation to study the behavior of the system, but it's using our method, we can do that. And we're able to do more than simulation in many other things. So for example, here, we compute the phase diagram indicating under which parameter range the system is in one state. So on the left figure here, blue indicates the system is in monostable regime, and red indicates the system is in bistable regime. Here, we are changing the parameter. Mu I means the connection strength between the inhibitor neurons, and mu E means the connection strength between the excitatory neurons. On the right side, we have another figure. In this figure, we are varying the number of neurons of the network, the bistable network, and we see what is the threshold value for the system to behave bistably, assuming a fixed ratio between the excitatory and inhibitor strength. Interestingly, we found that the critical weight scales approximately as 1 over square number of neurons, similar to the scaling defined formally in the balanced thermodynamic limits. In this limit, inhibition and excitation cancel one another on average. As a result, neuron activity is driven by fluctuations in the inputs. So 1 over square root of k scaling ensures that the neural variability is preserved in a large k limit for independent inputs. We also observe a very similar phenomenon in our RMF calculation in our model. This is because neural variability is an invariant of the dynamic at the bifurcation, where network starts to alternate between the nearly individualized up and down states. Preserving this variability throughout network size in RMF limit naturally requires 1 over square root of k scaling, which is remarkable in our in this case. So, okay, is there any more we can do? Yeah, probably yes. We have some preliminary results showing that we can potentially relate the transition rates of the up and down state in the bistable regime to the quantity x divided by the standard deviation of x. This kind of mimics the Arrhenius law. This is very surprising because our stationary model can potentially predict some dynamic quantities like the transition rate between two stable states. This is still ongoing work, and we only have some numerical evidences here. So we can see that as we change the parameters of the system, mu E here, here we can see the simulated value goes asymptotically onto a straight line. That means if we somehow find a formula for this straight line based on the parameters of our system, we are able to predict this transition rate just by looking at these stationary quantities of the network. Okay, that's all my talk. Is there any questions?
Thank you very much for this interesting talk. Are there questions in the audience?
I have a question, if I may.
Mm-hmm.
Can you hear me?
Yes.
Okay, so you show, so that's a very nice approach you are introducing with replica-mean-field approaches. I think it's really great. But I would like to understand if you show the simulation of the B-stable case, could you please show it to us again? Simulation of the B-stable case. Yes, this one. Mm-hmm. So you have the intervals in which you are in the phase up is intervals in which you are in the phase down. Well, yes. Since this is metastability, you would expect this law of this period to be approximately exponential, and this period to be the length of this period to be unpredictable. So my question is it possible to use the replica-mean-field approximation to derive things like the law of an interval, not only the law of the post at certain time, but the law of a period of time in which you are in a phase or another? Is this possible with the replica-mean-field approach?
So if I understand correctly, your question was if it's possible to find a relation between the state switch interval.
No. My question was has to do with the result Morgan proved the first talk. So we expect that the law of each one of the periods before you alternate. So you look at the first up period. So we would expect that the length of this to be to have a law which is approximately exponential. So the question is how to prove it in the model. So Morgan did it using certain approximations. So my general question is it possible to prove results like the law in which we say in the up phase, for the first up phase is approximately exponential? Can we prove this using the replica-mean-field approach?
No, I don't think this can be proved in the framework of the replica-mean-field limits because in this framework we are dealing with totally stationary quantities, while this is not stationary quantities. I think so. One possible direction is to start from like some sort of extreme event analysis, something like that. But I think it's not possible to deal with that in this framework.
Okay. So thank you.
Thank you.
Yes, thank you for your presentation. I would like to ask a naive question. I'm under the impression that you have this finite size network that you want to understand, and you make an infinite number, correct me if I'm wrong, an infinite number of copies. And by looking at this infinite number of copies, you claim that you get more information about the finite size network than if you would analyze it by itself. Do you let the number of neurons in the finite size network grow to infinity as well? I'm not sure I understand all this.
Oh, yeah. Sorry, it was my bad. Basically,
I missed Taifumie's talk on Mondays.
Oh, so basically the idea of replica-mean-field limit is, so the one I just showed you is a conceptual understanding of how what RMF limit is. But mathematically, what it does is it changes this point process of other neurons to a Poisson process. That's what it does mathematically. So if we want to understand it conceptually, we are kind of map a finite size network into an infinite number of the same replica. and each spike within the entire network is randomly dispatched to another one across all the replicas. So when we increase the number to infinity, the number of replicas to infinity, the correlation between between each pair of neurons disappeared. And we are entering a regime where we can ignore the correlation between neurons, and so we can approximate this point process of other neurons by a custom process and making this equation tractable mathematically. Does that answer your question? Or
let's thank again our speaker and go to the next.
thank you.